Section 11.3, the dot product. This is a very interesting section where we learn about a product between vectors. We know how to add vectors, but we haven't talked about multiplication of vectors. And there's more than one way of multiplying vectors. The dot product is one of them, and it has very interesting applications. So what we'll learn is to calculate the dot product. There's two ways of doing that, which is one of the reasons why it's so useful. We can find it in one way and use the other. Both ways are useful for different things. We're going to learn about its properties. It will allow us to find the angle between two vectors and also understand the notion of an orthogonal projection. So orthogonal projection is kind of the shadow of a vector onto another if you project perpendicularly. So here we can see that's a right angle. So this vector is projected orthogonally onto the long one, and the result is this short vector here. So you can see how this is linked to the angle between the two vectors, among other things. And then we're going to have one physical application with the concept of work in physics. So let's see the definition of the dot product. If you have two vectors in the plane, they are u1, u2, v1, v2, then the dot product is the product or the sum of the product component by component. So u1, v1 plus u2, v2. In 3D, in space, this is the difference in space and in the plane, what you do is you multiply component by component and you add again, so it's u1 v1 plus u2 v2 plus u3 v3. So you can see something that's interesting about the dot product, not interesting in the sense that it's valuable, but something that is worth noting, and that is that the dot product yields a scalar or a number. Scalar means number. So it's not, if you take this product of two vectors, you don't get another vector, you get a number instead as the output. For that reason, the dot product is also called the scalar product. Some of the properties, it's commutative, u dot v equals v dot u. You can convince yourself of that quite easily if you look at how it's defined. If we take v dot u, then it will be v1 u1 plus v2 u2 plus v3 u3. So since the product with numbers is commutative, then the dot product is also commutative. Distributivity, also c times u dot v is equal cu dot v, and it's also equals to u dot cv, which we will be able to convince ourselves of when we see the second way of defining the dot product geometrically. 0 dot a vector equals 0. Important here to notice that this is the vector 0, whereas this is the scalar 0. And again, it's easy just to see why this is true, because if it's 0 dot v, then we'll have 0 times v1 plus 0 times v2 plus 0 times v3. Last but not least, the dot product of a vector with itself is equal to the magnitude squared. How is that true? Well, if we take the dot product of a vector with itself, we'll have v1 v1 plus v2 v2 in 2D plus v3 v3 if we're in 3D, and that's v1 squared plus v2 squared plus v3 squared if we're in 3D, and indeed it's the same as the magnitude squared. Which tells us, in fact, that if we have a dot product in math, then we are always able to discuss what the magnitude is. If you give me a dot product, I automatically receive the concept of magnitude at the same time. So how can we find the dot product of u and v here? Very easy. 5 times negative 3 plus 4 times 8 plus 4 times 7 equals 13, and that's it. So there's a second way of defining the dot product. We define it in one way, and then we discover through a theorem that it is equivalent to another way. And this is that the dot product of two vectors is equal to the magnitude of the first vector times the magnitude of the second vector times the angle or cosine of the angle between them. The proof is quite interesting. It uses the law of cosines, and you can find it in the textbook if you're interested. But what's really interesting is to have two ways of finding u dot v. Sometimes one way will be easier than the other, and then we can use our result and reapply it in the second way. And we'll see that right now. For example, what is the angle between u and v? This is not an easy question at all, but we can find the angle just by dividing by the magnitude of u times the magnitude of v from here. Cosine theta equals u dot v over magnitude of u times magnitude of v. So we're going to be able to find u dot v using the definition, and then use the theorem to find cosine theta, and therefore theta. So what is u dot v? It's 3 times negative 4, plus negative 1 times 0, plus 2 times 2. The answer is negative 8. Magnitude of u is 3 squared plus 1 squared plus 2 squared, so it's the square root of 14. Magnitude of v is the square root of 20, and I plug everything in, I get cosine theta, and then I get theta, 2.069 radians, or approximately 118 degrees. So that alone is enough to tell us that the dot product is a fantastic tool, because finding angle between vectors might not always be easy. And this works in any dimension. Give me two vectors in 5 dimensions, I can just do exactly the same. It's just going to work perfectly. Another mathematical application is the idea of a projection. If you want to project a vector onto another, the dot product is going to help doing that. So this is the projection. Let's say I have u and v, and I want to project u onto v. I have to go down perpendicularly to v until the vector reaches v. And the projection is the vector starting here and ending there. So the projection is a vector. So this is not quite the same as this drawing here. Here, I'm just saying that this length, so the length of the projection would be magnitude of u times cosine theta. So how do we get to this formula? So again, I repeat, the projection is a vector. This is a vector, and how do we get that? It's u dot v over the magnitude of v squared times vector v. The reason, if we go back to the definition or the theorem for u dot v, we can divide by the magnitude of v, and we get u dot v over magnitude of v equals magnitude of u cosine theta. This is the length that is represented in green here. So we have a great first step, because in order to find the vector that has this kind of green stem here, we want that vector to have that magnitude. So this is excellent information to know that the projection I'm looking for has this magnitude. And so how can I now find the vector if I know its magnitude? I just want to multiply this by the unit vector in the direction of v. And this is it. V over magnitude of v is the unit vector in the direction of v. So if I multiply by the magnitude I want, I get what I was looking for. Magnitude of v times magnitude of v together explain why we have magnitude of v squared. And the reason why v is on the side here, isolated, is because this whole thing is a number. This is a number, and then times the vector v. So the output is a vector. So rather than just applying this exercise immediately, we have an exercise that is just a little bit harder, where the question is, how much of u is perpendicular to v in this example? So vector u is like this, vector v is like that, or vector v is up to here, notice in this example that the projection of u onto v is the red vector. It's longer than vector v. That's totally possible. So this is the standard example. We often take u shorter than v to make the sketch nicer, but if u is longer than v, then it's totally fine. We project on kind of the extension of v. There's also another situation if you have u like this and v like that, then the projection would be, this would be the projection. So it's the extension of v on the other side. Well, this should be a straight line, of course. And always, this is a right angle. So how are we going to find the amount of u, the component of vector u that is perpendicular to v? What we're going to do is we'll first find the projection, and then if you have the projection, then you can do projection plus perpendicular equals u. So to find the projection, we'll just apply the formula u dot v over magnitude of v squared times v. This is what we get, and we find that the projection of u onto v is 8, 6. It happens to be just exactly twice vector v. So now the question is 8, 6 plus what equals 5, 10? 8, 6 plus what equals 5, 10? And the answer clearly is negative 3, 4. Last thing, work. Work is defined as the product of the displacement with the force in the direction of the displacement, and the unit of work is joules. So here's a straightforward example. We have someone pulling on a rope from the top angle of a barn door, and as that person pulls, the door slides horizontally until it is closed. The distance that the door slides from point P to point Q is given here, 12 meters, or up here, 12 meters. I guess the original example had feet, but let's focus on meters. And the person is pulling with a constant force of 100 Newton, but at an angle of 60 degrees. So quite a bit of the energy here is lost, if I can say. So first we can find the projection of F onto PQ. That is actually quite easy just using geometry, because we know that the projection would be that vector here, and it's easy to figure out that it's 100 times cosine 60 degrees, so it's 50 newtons. Since PQ is 12, we find 600 joules. If we want to use the formula in all its beauty, just because not all examples are going to be that easy, then this is what it looks like. It's the projection of F onto PQ times the magnitude of PQ. So this is what you would do: u dot v over v squared times vector v. And once you do that, you can just multiply by the magnitude of v, which is 12, since v is 12, 0, and of course you get the same answer in the end. So that's it for 11.3, and it's a material that we will continue seeing over and over again, not just in this semester, but also in linear algebra next semester. Extremely, extremely important section.